We're continuing now in section 0.3 on mathematical induction. We've already talked about the well-ordering principle that said every non-empty subset of the natural numbers contains a smallest element. Obviously, the natural numbers have a smallest element in the number 1. Well, using the well-ordering principle, that was part of the proof of the principle of mathematical induction. I'm not going to prove it. I'll mention the proof in just a couple of minutes, though. Theorem 0.8, the principle of mathematical induction, a very powerful proof technique, especially if you are a computer scientist and analyzing algorithms. Well, let's suppose that P of n is a statement that uses the variable n for all n in the natural numbers. So we just defined an infinite number of statements. P1 is the statement P when the variable n is equal to 1, and so on. Well, we would like to prove that all of these statements or propositions, we'd like to prove it's true for all values of n. You obviously can't write out an infinite number of numbers. So mathematical induction gives us a beautiful way to prove that infinite number of statements. And here goes. If these two things hold true, then we're done. If the first one says, if P1 is a true statement, that could be very simple to prove. So if P1 is a true statement, and the second one is, if for all k in the natural numbers, this is true. If pk is true, then the next one is true, pk plus 1. And that'll be a simple algebra proof. You arbitrarily pick the value of k, and you assume that pk is true. Using that, then, you see if you can deduce that pk plus 1 is true as well. So it could be very, very simple. Maybe a few algebra statements is all you might need to do. So if that's true, and this is true, then Pn is a true statement for all values of n, for all of the natural numbers n. This part 1, this is frequently called the base case. And I'll mention this later, but it's possible that your Pn, which is your infinite number of statements, P1, P2, P3, it's possible that it's not true for P1, but it's only true for P2 and P3 and on. In that case, P1 would not be your base case, it would be P2. Okay, well, I'm not going to write out the proof of this, but the proof uses the well-ordering principle and something called proof by contradiction, which we may already have mentioned. I'd like to review what proof by contradiction is, since it's an excellent proof technique that frequently is easier than the alternative direct proof. Well, many theorems are stated in the form of P implies Q. If 2 is divisible by 2, then 2 is an even number. That was a very simple statement. It's a true statement. So many theorems are in this form. Proving them might be in the direct way might be difficult. So, and by the way, let me remind you what this means, P implies Q. I already stated it once, but it means if this left-hand side variable is true, then the right-hand side variable is true. If P is true, then Q is true, and that's all it's saying. And if you remember the truth table, maybe I should squeeze it in here real quick. For P implies Q, we do all the possible values for P and Q. True, 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 false, false, true, false, false. And we find that most of these are true. This is true. This is the only false one. And the justification for that is, well, first of all, just memorize it. But I remember learning in high school, my algebra teacher said, the statement, if I have $50 in my pocket, I'll take you to the movies. Well, the only time that statement is false is if I'm telling you a lie. If I actually have the $50 in my pocket, but I don't follow through, I fail in taking you to the movies. That's this. I have the $50, I don't take you to the movies. That means this original statement is false. If I have the 50 and I take you to the movies, it's true. I didn't lie. If I don't have the $50 in my pocket, I didn't really tell you anything. I only told you that if I have the $50, I'll take you to the movies. So I'm not lying to you. Therefore, these last two, it's true whether or not I take you to the movies, because I didn't have the $50 in my pocket. So this is the only time when an implication is false. All right, so the proof by contradiction, what we're going to do is say, suppose this is the case, and we derive a contradiction, which tells us, if we derive a contradiction, it tells us that this is impossible. It's impossible for this to be true and that to be false. Okay, so here, let's see. To prove if P is true, then Q is true, we may do the following. And this, my first statement in a proof by contradiction, is typically to the contrary, or maybe for the purposes of deriving a contradiction. Suppose P is true, I'm abbreviating it, P equal T is what I mean for P is true, and Q equals false. And then we just, through algebra or whatever, we derive a contradiction to show that that's not possible. That contradiction could be something like, well, we're assuming that P is true and Q is false. If we use logic statements and we come up with P equaling false, that's a contradiction. Or if we end up saying, oh, that means Q is true. Well, Q can't be false and true at the same time, so that's a contradiction. Or something silly like 1 equals 2. Any contradiction. Any contradiction will say, this thing that we supposed or assumed at the beginning is impossible. And that's all you have to prove in order to prove P implies Q. Okay, let's take a look at an example of a statement that we're going to prove by contradiction. And if you have seen, prove by induction. And if you've ever learned about induction before, then you will have seen this. This is almost always the first proof you learn by contradiction. Example, let's prove that the sum of the first n integers is n times n plus 1 over 2. So you could say that, maybe I'll do this, this is our proposition indexed by n. So if n is 10, this proposition is 1 plus 2 plus 3 all the way up to plus 10 is equal to whatever we get, 10 times 11 over 2. We're going to prove that statement is true by induction. Well, the proof, I'll make a note we're doing it by induction, although that would be obvious to me, especially if you have something called a base case. And then in the second step, we frequently call the induction assumption or induction hypothesis. By induction, the base case. For this case, it is actually n equals 1. And all we need to do is prove that P1 is true. Now, if you haven't seen this before, the left-hand side when n is equal to 1 is nothing more than the number 1. It looks like it has 1 plus 2 plus 3, but it only goes up to n, and n happens to be 1, so that means that this whole left-hand side is just 1. 1 equals, and I'm putting a question mark there, does 1 equal 1 times 1 plus 1 over 2? And that's 1 times 2, 2 over 2, that's 1. So I put a check mark saying I verified the base case is true. Now we will move on to what we call the induction hypothesis, the inductive assumption, where we are going to say, suppose that pk is true for some arbitrary natural number k. So pk is 1 plus 2 plus 3 up to k is equal to n plus 1 over, sorry, I changed variables, so I have to use k here. K plus 1 over 2. And frequently some students, and sometimes I, will not even change the variable here. We'll just use the variable n, just like it is up here. So assume that this box is true, and then prove that the n plus 1 case is true. But since I use the variable k, this would be pk, and so I'm assuming that's true for some natural number k. Now I need to prove, and this may be the most difficult for some students, just define what pk plus 1 is. And maybe this isn't really part of the proof, but I'm going to go ahead and, just for our own notes, put in brackets here what pk plus 1 is. Well, that means I have to go from 1 plus 2 plus 3 all the way to up to k plus 1. So I've got 1 plus 2 plus 3 plus all the way up to k, and then I need to go one more. I'll put parentheses around it just to distinguish it. pk plus 1. And then, instead of putting in n here, that n is now k plus 1. Instead of putting a k plus 1, instead of n plus 1, I've got k plus 1 for n, plus 1 more, which is k plus 2 over 2. So this is sometimes the more difficult step, one of the more difficult steps in a proof by induction. You have to know what you want to prove. So this is the statement pk plus 1 that we have to prove is true. So let's notice what we do know about pk plus 1, or what we know about the left-hand side of the statement pk plus 1. Maybe I'll put a colon there. This whole thing right here is the statement pk plus 1. So notice that this left-hand side, 1 plus 2 plus 3, all the way up to k, and then k plus 1. I can't just write that because we have to prove this. But what do we know about this? Using our induction assumption, we're assuming that this is true. So what I just circled, or put the cloud around, is the sum from 1 to k, and that's equal to k plus 1 over 2. That's equal to k plus 1 over 2, and then plus k plus 1. And I'll note that that's by the induction or inductive hypothesis. This is the inductive hypothesis. We just supposed that's true, our hypothesis. All we need is 1 or 2 steps of algebra to show that this is indeed equal to that. So we get k plus 1. I'm going to get a common denominator. So if I need this to have a 2 as a denominator, I'm going to have to multiply this by 2. So plus 2 times k plus 1 all over 2. So all I did there is just get a common denominator. Write it as one fraction. And that's equal to, well, notice this is a sum of 2 products, and each one of them has a factor of k plus 1, so I'm going to pull that out. It leaves us with a k plus 2 over 2, and that's the end of the proof. That's exactly what we needed to come up with. All right, get ready, we're going to do one more example